Our method effectively simulates contact with friction in manipulation tasks. We simulate contact using a continuous model of compliant forces with regularized friction. This allows us to cast the problem as a system of ODEs. We evaluate the performance of implicit integrators for these stiff systems and design a method that allows the implicit Newton solves to succeed even when using large time steps. Implicit integrators use Newton's method to solve for the next v. With friction, the residual slope changes drastically between sliding and stiction. In this example, we start from v equals v0 in the sliding region and try to reach v star in stiction. At v0, Newton's method follows the slope and arrives at v1, which is on the other side of the stiction zone. At v1, we follow the slope again and land on v2, which is on the original side. This will only oscillate between v1 and v2 and never converge. Let's start again at v0 and make a slight modification this time. Our method uses the system's dynamics to backtrack the Newton step so that when it tries to jump across, it stops in the stiction region. From here, the slope is more accurate and we find the root quickly. Consider a simple gripper grabbing and shaking a mug. Strong disturbances during a manipulation task are emulated by shaking the mug vertically. When the grasp transitions between sliding and stiction, a traditional implicit Euler scheme needs to take smaller time steps to ensure the convergence of the implicit Newton solve. This causes the short pauses in the video along with the jagged plateaus in the red line. Our transition-aware line search can take larger, fixed time steps and thus runs more smoothly and faster. We evaluated the performance of our TAMSI method on a complex manipulation task using a 16-DOF Allegro hand with multiple points of contact. We demonstrate the robustness of our TAMSI method to simulate a manipulation task with vigorous shaking motions emulating disturbances. A Kuka-Iwa arm is commanded to pick up a bottle, execute a shaking motion, and set it down at a specified position, where force feedback is used to assess grasp quality as well as task completion. We show that our framework is ideally suited for prototyping controller processes for manipulation that seamlessly transfer to reality.